Okay, so let us now apply these concepts to think about our initial problem of portfolio optimization. So whenever an asset is acquired, recall that the rate of return is typically something that is uncertain. So that makes sense to kind of think the rate of return to be the random variable that we are interested in. So we are going to summarize the uncertainty regarding the rate of return by looking at several of its descriptive statistics. So one thing would be the expected value. So that is going to be denoted by expectation of R or R bar. Then you have got the variance of the rate of return, which we are going to call sigma squared, which is equal to expectation of R minus R bar squared. And finally, we would also often need to recall what are the covariance of the rate of return of a particular asset with the covariance of the rate of return with the other assets, right? So all of these things will come up as we'll see. So let's consider some examples just to fix some ideas. So suppose that you have got 1 unit of money and a fair die is going to be rolled. And depending on the number that turns up, this 1 unit of money is going to lead to a payoff of 0, 4, -1, 2, -1, or 3. So how do we interpret these numbers? So suppose 1 turns up, then you're going to get a payoff of 0. If 2 turns up, you're going to get a payoff of 4. If 3 turns up, you're going to get a payoff of -1. If 4 turns up, you're going to get a payoff of 2. If 5 turns up, you're going to get a payoff of -1. And if 6 turns up, you're going to get a payoff of 3. Okay. So clearly, because there is uncertainty about which number is going to turn up, there is the payoff itself is uncertain. So let's denote the payoff as the random variable Q. So we can calculate what's the mean and variance of this Q. So the mean of Q, which we denote by Q bar, is equal to 7/6. In order to see this, basically each of these outcomes are equally likely because it's a fair die. So we have got 1/6 times the sum of these things, right? So if we add up, we get that 4 minus 1 is 3, plus 2 is 5, minus 1 is 4, plus 3 is 7. So that's where we get 7/6. And similarly, we can calculate the variance by looking at our usual formula, expectation of Q square minus Q bar square. We have already calculated Q bar, and expectation of Q square is very easy to calculate here as well, right? We'll just square these numbers, sum them up, and then divide by 6 to get it. And if you do the calculations, then the variance turns out to be approximately equal to 3.81. Now, this is about the payoff, right? The amount of money that you are going to get. How do we move from here to the total return? Well, the initial investment was 1 unit, right? So therefore, the payoff is the same as the total return. And so therefore, Q is equal to R, right? And so this is also calculates the expected return, the total return, and the variance of the total return. And if you want to move from the total return to the rate of return, remember the relationship is the rate of return is the total return minus 1. So we can easily calculate the expected rate of return, which is just 7/6 minus 1. So 1/6. And the variance is going to be the same as that one for total rate of return, right? Why? Because remember, variance of small r is the same as variance of r, right? Because this -1 is just a constant. And so therefore, the variance of the rate of return is the same thing that we had derived previously as well. Okay, let's look at another example. This is a bit more complicated. So imagine that, again, you have a fair die that is rolled. And now, instead of looking at each of these numbers on top as the elementary events, the events are a bit more complicated. So you've got event A, which corresponds to either one of 1, 3, or 5 coming up on top. Event B corresponds to 4 or 6 coming on top, and C corresponds to 2 coming up on top. So roughly speaking, the idea is that A represents the event that an odd number shows up, B represents the event that a even number shows up, which is not a prime number, and C represents even number showing up, which is also a prime number. Okay. And imagine that one is allowed to bet different amounts on the different events occurring. In particular, the payoffs are determined as follows. So if one invests 1 unit of A and the event A occurs, then the payoff will be 3. But if the event A does not occur, then the event is going to then the payoff is going to be 0. Again, if one invests 1 unit on B, then the payoff will be 2 if B occurs, and it's going to be 0 if B does not occur. And if one invests 1 unit on C, then payoff will be 6 if C occurs, and zero otherwise. Okay, so this is how the payoff of this particular bet, if you like, is given. Okay, we can calculate the expected total returns. So the return, if you put in the money on event A occurring, is given by half into 3 plus half into 0. Where do we get the half from? So remember, it's a fair die, so the probability of event A happening is 3 by 6 or half. Okay, so if event A happens, you get 3, so that's where you get the 3 from here. And if event A does not happen, which happens with, again, probability half, you get 0, so you end up getting 3 by 2. This is the total payoff, and the investment was 1, so therefore this is also the total return. Okay. You can also calculate the expected total return from B in the similar way. Remember, probability of B happening is 2 by 6, and probability of C happening is, by the way, 1 by 6, which we'll also need. And then you can do the calculation in exactly the same way, so that the expected total return, if you put in this 1 unit of money on event B, is equal to 2 by 3, and the expected amount of total return, if you put 1 unit of money on event C, is equal to given by 1 by 6 times 6 plus 5 by 6 times 0 is equal to 1. So this is how you calculate the expected total returns. You can similarly calculate the variances. So again, very similar. So with probability half, you get, remember, 3. So therefore now if you want to calculate the expectation of the square, this 3 will become 3 square. 9, and the other case is 0, so we don't need to consider it. So that multiplied by the square of the expected total return, so that gives you the variance, right? So sigma square A is equal to 2.25, sigma square B is 0.89, and sigma square C is 5, right? So these are hopefully pretty straightforward. Now, it turns out that the returns are also correlated, okay? And the reason is pretty simple, that if you have got one of these events kind of happening, then the other one is not going to happen, right? So therefore, we can actually think about exactly what are the covariances also. So how do we calculate the covariances? Well, the first thing to notice is that the value of the products, such as expectation of R1, R2, or expectation of R1, R3, and expectation of R2, R3, all of them are equal to 0, right? Why is that the case? Because suppose that actually event 1 has happened, right? Or rather, event A has happened. Then in that case, event B clearly cannot happen, right? Because these are mutually exclusive. And so if you are getting some money from A happening, then you are not going to get money from B happening at the same time, right? And so therefore, these are going to be, the products are going to be 0. And so therefore you end up just, if you want to calculate the covariances, you end up just looking at the product of these things, right? So the covariance sigma AB, so this, by the way, 1, 2 should be AB, 1, 3 should be AC, and 2, 3 should be BC. So sigma 1, 2, sigma AB is equal to nothing but the negative of RA bar, which is 3 by 2, multiplied by RB bar, which is 2 by 3. And so that's why you end up getting -1. And similarly, sigma AC is going to be negative of RA bar times RC bar. And so you end up getting -3 by 2 and so on. Why negative? Basically, here we are using the formula that the covariance is expectation of, let's say, for this one, we have got that sigma AB is expectation of RA, RB minus expectation of RA multiplied by expectation of RB. We already know that expectation of RA, RB is equal to 0. And so from therefore, we know that from there, it's just the negative of the product of the expectations, right? So that's how we get to these calculations. Okay, so what does this imply in terms of the portfolio mean and variance? So suppose that there are n assets with rates of return given by R1, R2, and Rn. And suppose that these assets have expected values, which are given by R1 bar, R2 bar, and Rn bar. So we are going to form a portfolio of these n assets using the weights Wi. So what is the rate of return of the portfolio? We already know it's the weighted average of the rate of return of these individual assets. So therefore, the portfolio rate of return is given by W1R1 plus W2R2 plus WNRN. And the expected rate of return is given by the weighted average of this expected rates of return of the individual assets, where the weights are again the ones that are given in the portfolio. can also calculate the variance. This is a bit more complicated formula compared to the one for the expected rate of return. So denote the variance of the rate of return of asset I by sigma I square, and the variance of the rate of return of the whole portfolio by sigma square. So here the relationship between sigma square and sigma I square also needs to take into account the covariance of the different rate of return of the assets, right? So for example, sigma ij is the covariance of the rate of return of I with that of j. So the formula for sigma square, which is the one that we care about, the variance of the rate of return of the portfolio, is given by expectation of r minus r bar square. Now, R we already know is summation Wi Ri from here, and R bar we also know is summation Wi Ri bar, right? And now if you kind of expand this and do a bit of simplification, you can show that this actually ends up becoming summation over ij from 1 to n Wi Wj into sigma ij. Okay, so this is a simplified expression for the variance of the portfolio in terms of the different weights of the assets in the portfolio and the covariances. In case you are wondering what happened to the variances, remember that this also allows for when we are doing the summation, we'll also need to consider the case where I equal to j. And in that case, we'll end up in that particular term being Wi sigma square, right? So remember, sigma ij is equal to sigma square if you have got I equal to j. Okay, let's look at an example just to, again, fix this idea. So suppose that you have two assets with the first asset's expected rate of return being 0.12, the second asset's rate of return being 0.15. This is the expected rate of return. The standard deviations being 0.2 and 0.18 respectively, and the covariance being equal to 0.01. Okay. Imagine that we form a portfolio with weight of 25% on asset A and 75% on asset 2. And so therefore, the mean of the portfolio is given by the weighted average of the this rates of return. So it's going to be 0.25 multiplied by 0.12 plus 0.75 multiplied by 0.15. Okay. And if you do the calculation, that's equal to 0.1425. And the variance, we are going to apply this formula. So let's see how it applies. So remember here, n is equal to 2. And we have got W1 is equal to 0.25, W2 is equal to 0.75. And we also have the different sigmas that we want, right? So the first term will be when we have got I equal to j equal to 1. Okay, so then in that case, the two weights are the same and it's equal to 0.25. And we are going to multiply that by sigma 1, which is sigma 1 square, right? And so therefore you see here the 0.2 square. The second term would be when you have got I equal to 1, j equal to 2. So you end up getting 0.25 multiplied by 0.75. So that those are the two weights. And you multiply it by the covariance, which is given by this 0.01. Okay, so that's how we get this term. Another term you will get from I equal to 2, j equal to 1. So therefore, again, this is going to be the same. It's symmetric, right? So 0.75 into 0.25 into 0.01. And finally, the last term is going to come from I equal to j equal to 2. So then the two weights are 0.75 into 0.75. And then you get the variance, which is the 1.18 square, right? And so if you do the calculation, this will turn out to be 0.0245, right? So that's how you can calculate the variance. Okay. One of the applications of this formula of the variance that we calculated, we can actually take a deeper look into the phenomena that is known as diversification. So it's a very simple idea. It says that if you have a portfolio with only a few assets, that is subject to more risk compared to a portfolio which has more assets, right? So here we are thinking of measuring risk via variance, right? So the idea, if we want to say that, we can reduce risk, that means that the variance of the return of the portfolio can be reduced by including additional assets in the portfolio. So this is exactly what is known as diversification. And we can actually take a deeper look using the formulas that we have just discussed. Okay, so let's first consider the case where you have got many assets and all of these are mutually uncorrelated, right? So what that means is that we are going to consider, let's say, n assets, all of which have zero covariances, right? Now, So sigma ij is equal to 0 for I not equal to j. So the rate of return of each of these assets, let's assume it has the same distribution. So in the sense that it has the same mean m, and the variance is also given by sigma square for each of these assets. And we are going to construct a portfolio by taking equal portions of n of these assets. Okay, so that means that the weight of the different assets in the portfolio is given by 1 over n. Okay, so what's the overall rate of return of this portfolio? That's going to be summation over I from 1 to n, WIRI. So here WI was 1 over n, so we can take the 1 over n outside. So the rate of return for the portfolio is equal to the average rate of return of this individual assets, right? And what about the mean rate of return? Well, if we take the expectation on both sides, we know that each of the assets has mean m. So therefore, the overall portfolio is also going to have the same expected rate of return, right? That's going to be equal to m. And notice that this does not depend on how many assets you have, right? This expectation that we got, the expected rate of return for this portfolio, that is independent of n. Okay. What about the variance? So if we do the calculation for the variance now, and remember, this is the one case where you have got that the assets are uncorrelated. So then this variance of R is going to be 1 by n square, summation over I from 1 to n sigma square, right? So sigma square is a constant. You are adding up n of those. So this whole thing, the summation into summation sigma square becomes n sigma square, and you can cancel one of the n's so that you end up that the variance of R is the sigma square by n, right? So what you get from here is that as n is going up, this variance is actually going down, right? So this is the idea that if you kind of like the variance of the return can be reduced by including additional assets, right? So it makes sense here, right? And we can also actually see how such a graph would look like. So here we have plotted not the variance, but the standard deviation, which is very closely related. And we have taken sigma to be 20%, and we have 0% correlation between assets. So the assets are uncorrelated, and we are seeing the effect of changing the number of assets on the standard deviation, right? So as you might imagine, it makes sense that if you have got sigma equal to 1, then in that case, we have got the standard deviation of the portfolio is going to be the same as the standard deviation of the asset. But as the number of assets is going up, this we can see is actually going down, right? So by the time you reach, let's say, n equal to 100, then the standard deviation, which is going to be sigma divided by square root of n. And so therefore, it has actually gone down to 2%, right? And in fact, if you further increase it, this will keep on going down. Okay, so this is the basic idea behind diversification. Now, one question to ask is that, okay, we have assumed here that all the assets are uncorrelated. What happens if the returns of the available assets are correlated? What is the result we get in that case? So let's use the formulas that we have derived to also think about that. So suppose again, as before, that each of the n assets has a rate of return with mean m and variance sigma square. So we are keeping this unchanged, but the only thing that we are now changing is that we are allowing for the covariance to be not equal to 0. So imagine that again, everything is symmetric so that the covariance between Ri and Rj is given by 0.5 sigma square. Okay. And we are going to construct a portfolio as before by taking equal portions of these n assets. So you can show that the mean is going to be the same as before. So that's going to be equal to m, which is independent of n. What about the variance? Well, we are going to use this formula of variance that we had seen before. So summation over I from j equal to 1 to n, wi, wj, sigma ij. Now both wn, I and wj here are equal to 1 by n. So that wi into wj always is equal to 1 by n square, and we can take that out of the summation. So we have got 1 by n square summation over ij sigma ij. So we are taking all combinations of I and j, where each of I and j can take the value between 1 and n, and we are adding up all the covariances, right? So we can actually divide it into two parts. So cases where you have got that I is equal to j. Okay, so this is the first summation. And the second summation has the case where you have got I not equal to j. Now, if you have got I equal to j, sigma ij is nothing but the variance, which here is sigma square, and you are going to have n of these terms. So this first summation becomes just n times sigma square. What about the second part? So this is the one where I is not equal to j. So therefore, sigma ij is the covariance term, right? And we know that the covariance is 0.5 sigma square. And how many of these terms are we going to have? Well, overall, we would have had n squared terms. We have already considered n of these terms. So therefore, the number of terms we are going to have is n square minus n, right? Now, if you simplify this a bit, so for example, if you expand this bracket, you end up getting sigma square by n plus 0.5 sigma square. And if you then divide this term in the bracket n square minus n by n square, you end up getting 1 minus 1 by n, right? Now, if you compare this expression with the one that we had got before, remember earlier we had just got sigma square by n. So here we are getting sigma square by n plus some positive term, right? So what that tells us is that the variance here is going to be higher compared to the case where you didn't have this covariance, right? And so we can also simplify this to end up getting 0.5 sigma square plus 0.5 sigma square by n, right? So the implication of this is that you can increase n as much as you want, but the variance is always going to be higher than 0.5 sigma square, right? Remember, in the previous result, we had that if you increase n enough, you're going to get that the variance is going to go down to zero eventually, or approach very close to zero. But here, doesn't matter how much you increase in, the variance is always going to be more than 0.5 sigma square, right? So this actually provides a lower bound on how low the variance can be reduced. And we can also see this graphically. So this is the same picture that we had as before. So we have got, again, 20% standard deviation of assets. The only difference between this picture and the one that you just saw is that the correlation between assets is different. So this picture that we had seen earlier had the correlation between assets to be 0%. And this we saw that the standard deviation was actually going down very sharply, right? In fact, even at 100, you had come down to 2% from the 20% that you had initially, and this is further going down. But here, if you look at the same thing, with the only difference is that the correlation between assets is no longer 0%, but is now 25%. You can see that while initially it was 20% as it was before, but now if you have increased the number of assets to 100, this is still around 10%, right? And in fact, this continues to be like that, right? So again, this actually, the rate at which this is going down has come down, and of course, it will never approach zero. Okay, so in this analysis, we made some particular assumptions, right? So we assume, for instance, that the expected rate of return is equal for all the assets. And so therefore, increasing the number of assets did not affect the rate of return for the portfolio, right? In general, we'll see that diversification may have the advantage of reducing the variance, but it also comes at a cost, namely that the overall expected return would also perhaps go down, right? And so therefore, it's not enough to just look at what is happening to the variance or the standard deviation. We also need to understand the effect of diversification on both mean and the variance of return. And this is in fact a motivation for one of the models that we are going to consider this week, which is known as the Markowitz model, where this trade-off between the mean and the variance of return is going to be explicitly considered. Having said that, still there are a couple of important lessons to learn from our simplified setup. So the first lesson being that if the returns are uncorrelated, then it might be possible through diversification to reduce the portfolio variance essentially to zero by taking n to be large enough. And secondly, if the returns are positively correlated, then however, it is much more difficult to reduce the variance. And in fact, there may be a lower limit to how low this portfolio variance can be returned, right? Just as we have seen before. So we are going to come back and discuss a bit more about diversification once we have understood a few more basic points.